In this video, we will comprehensively discuss the Rietveld refinement of XRD data in GSAS-II, which is a free Python-based software that utilizes the least square fitting for the refinement. How to download and install this software? I have already made another video tutorial as shown in the link above. Rietveld refinement is a method for analyzing the crystal structure of a material from its X-ray or neutron diffraction pattern, which was developed by the Dutch scientist Hugo Rietveld in the late 60s. In Rietveld refinement, a theoretical diffraction pattern is calculated from a model of the crystal structure and then compared to the experimental diffraction pattern. The model is adjusted iteratively until the calculated diffraction pattern matches the experimental one as closely as possible. The refinement process in crystallography is a careful procedure involving the adjustment of multiple parameters within the crystal structure model. These parameters encompass the precise position of atoms, the thermal vibrations they undergo, and the scale factor governing the intensity of diffraction peaks. Additionally, the Rietveld refinement method permits the incorporation of other factors capable of influencing the diffraction pattern, including sample microstrain and background scattering. However, it is to be noted that Rietveld refinement are not flawless and should be viewed as models representing the data in system under study. When dealing with highly complex crystal structures, laboratory X-ray techniques may fall short for providing accurate results. In such cases, advanced diffraction experiments such as synchrotron powder X-ray diffraction or powder neutron diffraction become necessary. These advanced techniques are crucial for determining complex crystal structures that involves factors like occupancy, minor impurities, thermal parameters, and other complex details. Let's start the tutorial. This is the X-ray powder diffraction experimental data of cobalt tetroxide CO3O4, which is a black antiferromagnetic solid material. This data has been acquired through the Panalytical Expert 3 machine. Let's first discuss the data that is required for the analysis and refinement. I will share the link to all this data in the GSAS project file in a zip folder, which can be downloaded via a link provided in the video description. This is the XRD powder data of CO3O4, in which we have our required data of 2 theta versus intensity in the text format. The input data format can be other formats like FXYE, GSAS, or RAW, etc. The next file is the parameter file, which can be acquired by running a calibration on the instrument using a well-known standard. This is used to generate accurate UVW profile parameters in an updated zero value for the instrument, which will be discussed as we go along the refinement process. In case the parameter file is not available, we are yet able to refine it with some known phases. Please note that when the XRD input data file and the parameter file have the same names, titles, and are located in the same folder, GSAS will automatically select them without prompting for a parameter file. For a given sample, in this case CO3O4, there are known phases like COO, COO2, COO3, and CO3O4. These phases can be easily downloaded from the Crystallography Open Database. These phases will not only help in sorting out XRD peaks of our sample from the background or artifacts, but will also be used to calculate the phase fraction of each phase. Let's open the GSAS-II software. Open a new project and save it at a desired location. Multiple windows will open in which the most important one is labeled as Data Tree. This is the window that controls the parameters in refinement, while the plot is displayed here in the plot window, and processes are executed here in the Bash window. Select Import Powder Data and then select the format and file of the diffraction data, which is in text format, and we let the software guess the format from the file. PyGSAS will then automatically prompt for an input instrument parameter file, and here it is. Here is a new entry in the data tree window labeled powder, and the name of the histogram is our input file. Under the Limits menu, we can select the start and end values in the range in which we intend to refine. As we are intending to refine the whole spectrum, we will keep the default full range values. In the instrument parameters, change the radiation wavelength to copper K alpha as it is our instrument source. Under the sample parameters, write the instrument name which is used to acquire the data. In our case, it is the Panalytical Expert 3 machine. Select the diffractometer type as Bragg-Brentano based on our instrument configuration. Untick the histogram scale factor box as when dealing with samples containing multiple phases, it is necessary to unselect the default option within the sample parameters. This is because the intensities of both phases cannot be effectively treated or scaled together. Instead, we should enable the phase fraction option within the specific phases settings located under the Data tab, and type in the correct goniometer radius if we know. Otherwise, leave this and the other values as default, which will be adjusted later if required. Now this is time to start with another histogram of possible phases in our sample. To add a phase histogram, select Import, Phase, go to From CIF file, and then one by one select each phase to refine. It is recommended to add and refine each phase one after the other unless we are sure that all the phases are there. As we know in our sample, both rock salt COO and spinel CO3O4 are present, so add them both. When asked to add it to the sample data, select the data and click OK. Once complete, we will now have another new entry in the data tree window labeled as phases, with the entry of COO to the phase histogram. Now add another phase of CO3O4. It prompts for the shift of origin. Select the GSAS recommended shift of origin option as it places the origin at the center of symmetry. Note that there may exist other phases as well. However, when such a phase is added which doesn't exist in our sample and refinement is performed, it will give Hessian SLQ error. When we select a specific phase, a window titled Phase Data for COO will open, displaying a lot of information related to that phase. Within this window, we will find several tabs, one of which is labeled Data. Click on the Data tab and select the Phase Fraction Refinement option with a default value of 1. This action permits us to refine the intensity of this particular phase. Repeat this process for all phases to ultimately calculate the phase fraction for each one. We are now ready for the first refinement. Under the section Controls, we can set the maximum cycles option to choose 10. This restricts the number of iterations to 10 of the refinement process on each refinement run. It is up to our choice whether to conduct fewer or more iterations for each run. The more the number of iterations, more will be the time required. Choose Data Tree and then click on Calculate and finally select Refine. The refinement process will start, and once it is done, we will see the weighted residual RW value. Ideally, this value should be 0 as it is the difference between the experimental and calculated pattern. However, a value lower than 10 is recommended. The more it will be close to 0, the more good will be the refinement and fit. In the first run, the RW value is around 20%, which is quite good. It might be higher during the initial attempt. When the program asks to load new results, simply click on OK, as we accept the refined results or otherwise. If at any point we perform a refinement and it makes things considerably worse, we have the option to reject the changes and continue the refinement with slightly altered parameters. When a refinement is done and we accept the results of achieving a minimum in the refinement, it is better to off that refinement option before the next one. This way our refinement process will not stuck elsewhere on our way to achieving the global minimum. In the data tree window, start by clicking one of the phases and then click on the powder item. This action is necessary to open another window that displays a histogram in our newly adjusted pattern. And finally, click the home button to see the full features of the plot. If we skip clicking on the phase first, we wouldn't see the legend with each phase details and the small colored marks indicating where we expect HKL reflections. Now, go to the GSAS-II plots. At the bottom of this window is a magnifying glass icon that allows us to zoom in on specific areas. Use this to zoom in on some of the primary peaks. Here we will notice several elements: blue plus marks representing experimental data points, a red line indicating background, green lines showing the calculated pattern, a teal line displaying the difference between experimental and calculated patterns, and vertical colored marks in red, blue, etc. denoting the expected peak positions for different phases. As we examine this, a few observations become clear. Firstly, some peaks are fitting more or less adequately, but their shapes and center needs adjustment. Secondly, some peaks are not fitting at all. Thirdly, There are some peaks which are not corresponding to the given phases in the samples. Such peaks may be attributed to the background or artifacts and are supposed to be excluded from the calculations to achieve a good fit. First, go to Data Tree and then select Border and click on Background. A new window will appear. If the overall shape of the background, not specific missing peaks, is incorrect, we can make adjustments by adding more terms to the Chebyshev polynomial. However, this is seldom necessary and usually 3 terms works well unless we have a significant amount of non-crystalline material in our XRD scan. The fewer the number of polynomials, the more realistic our fitting will be. However, in case of a bad background, we can increase the number of polynomials. In this window, there is also an option called Peaks in Background, which allows you to designate certain peaks as part of the background. Use this option only if you have a good reason to do so. Never try to force a pattern to fit a peak when you expect a peak for one of your known phases. In this particular case, the peaks we see come from our substrate and we do not know the exact phase of that material. Therefore, we will categorize them as part of the background. First, we will check and count the number of such prominent peaks. Thus, around 8 peaks are from the background. From the option Peaks in Background, select the number 8. Now we will find the position and intensity of the peaks one by one and will refine each of them for the best fit. We will write the intensity of a peak slightly more than the existing value to force it for a good refinement. Here, sigma and gamma are the mathematical parameters that are related to the shape of the peak. It is better to leave the sigma as default while changing the value of gamma to 8 to 10 for each peak, followed by a subsequent refinement. In case the RW value increases or something unusual happens, we will not accept loading the new data. Now, first we will run one refinement with our existing parameters, and if the results are good, we will tick the refine option one by one. As it has improved, so now we go for the refinement of each parameter. Double click on the peak position refine options to select and go to calculate and click refine. By magnifying the peaks, we can see that the intensities are not well fitted. So we do the same procedure with the intensities as well. And now we can see that with the improvement of intensities, the value of RW has reduced. Now to refine the shape of the peaks, gamma refinement plays an important role, so we refine the values of gamma only and leave sigma as default. we can see that no further improvement through the background correction is possible. Examining our plot, it is evident that the most significant errors are from both peak shape and peak location. Our initial focus will be on refining the peak location. For this, we go toward the phases and refine the unit cell. We will first do it for the COO phase and then for the CO3O4 phase. However, it is crucial to address the considerable room for improvement in peak shape. As we know, the diffraction profiles from laboratory diffractometers are a mixture of Gaussian and Lorentzian profiles. Here in GSAS, U, V, and W are the mathematical coefficients in the Gaussian function that controls the shape of peaks, as shown here in the equation. It is to be noted that U and W will be positive, while V will be negative for a standard Bragg-Brentano diffractometer upon refinement. It is better to refine the instrument parameters U and W one after the other to fit well the width of peaks. The role of V is not vital in the refinement, so we skip to refine it. X and Y are the coefficients in the Lorentzian function that controls the width of peaks as shown in this equation. In case there is no Gaussian sample broadening, S gamma equal to 0, and if there is no Lorentzian instrument broadening, XYZ equal to 0. The value of X and Y will also be kept as default without refinement. We can activate additional variables if it makes sense to do so. However, be careful not to turn on variables without a good reason. Although it might seem like it improves the fit, doing so without a solid scientific basis can lead to inaccurate refinements. In Rietveld refinement, thermal corrections to atoms in phases refer to adjustments made to the atomic positions and thermal vibrations of atoms within a crystal structure model to improve the fit between the calculated and the observed X-ray or neutron diffraction data. These corrections are necessary to account for the fact that atoms in a crystal lattice are not stationary but rather vibrate thermally due to their finite temperature. As the phase fraction of CO3O4 is high in the sample, therefore its refinement will have more contribution to the overall refinement compared to COO. Here under the atoms, we have the atoms of COO. If we click on the drop-down menu here, we see a list of refinement choices X, XU, U, F, FX, FXU, and FU. X will refine atom positions, U will refine their thermal parameters, F will refine their fractional occupancies, while XU, Fx, Fxu and Fu are just a combination of the above. For example, if we do Xu, it will refine the thermal and site positions, and Fxu will refine positions, thermals and occupancies. We will critically observe the RW value. If it lowers after the refinement, we will accept the reload of new refined data, otherwise not. If at any point we sense that the refinement process is deteriorating, not progressing as intended, or if we accidentally choose to reload data with a higher RW value compared to the previous iteration, there is no need to close and restart the entire project. Instead, we can simply navigate to the folder where we have saved our project. Within that folder, automatic .bake files have been generated at various intervals during the refinement. We have the flexibility to restart the project from any previous point in the sequence. Finally, as our fitting needs further improvement as the RW value is around 20%, inside phases we can select a given phase and refine the size and microstrain one after the other for each phase. Since this video has become longer, in the next tutorial I will guide you to the process of customizing this plot and exporting it as a figure suitable for publication. Thank you for viewing this in-depth tutorial. I appreciate your engagement and I encourage you to remain connected for additional tutorials that will be shared in the future. Your continued interest is valued and I look forward to bringing you more insightful content in the upcoming sessions.